Good evening and welcome back to the next episode. Quite a fun one today, actually. I've been building towards, I guess, smarter font rendering. So the previous project, I just had a bitmap that I used to draw letters like other sort of sprites, which works but isn't particularly clever. And really, what I would like to do is load textures from a TTF. Sorry, load fonts from a TTF file, generate textures, draw quads with those textures, and then you can draw text nicely and easily. With the sort of added limitation that, like everything else in the renderer, it's all pixelated using nearest neighbor sampling. Partly for simplicity, partly because I'm not going to make nice assets, so we're going to kind of lean into that sort of more retro look. And I didn't know how to do that. So in the previous video, we've got font atlas generation set up. So we've now got an image with our sort of font rasterizing a set of letters and saving a PNG with it on. And I've now got something working to pipe that through to the GPU and actually draw it. So if I now go ahead and run our program, you will see the letters look different than they used to. So we have a blue A and this kind of grey letter B. And if I go find our main.odin and we go find, I guess it'd be called drawable B, we can tweak these colours. Something like that. And the B gets pink. So that's pretty fun. Now, the way this is working is I've defined, where would this be? Probably was in renderer. I've extended my notion of drawables. So what we now have is, instead of just having textures and drawables with a position, dimension, and texture information, we now have textures and font textures, and we now have sprite drawables and mask drawables. So what we're going to have is the game state that determines what will be drawn to the screen will be used to generate a set of drawables. Those drawables know where they should be on the screen, basically, and how big they need to be, and what texture needs to be applied to them. They get dumped into these buffers, and we then generate our vertices and indices from those buffers. And because I've got them separated, the two can be treated differently. Now it's kind of step one. And you can see the kind of change down here, right? So push drawable. The person calling the function, I'm thinking this probably is neatest, is you don't need to know as you're doing your logic. So if a thing in the game switches from being a sprite drawable to a mask drawable, you call the same code, right? It's all handled internally within the kind of renderer code to work out how to draw it, which I think is neat. So we populate those two buffers full of drawables, and then we're going to generate our vertices and indices to actually pass it off to the GPU. Now, I've done a little scribbling to remind myself how it used to work and how it now works, because I've learned a few things doing this. So I thought this might be an easier way to get through it. And I'll sort of jump back and forth to reference the code as and when. So the old way I was doing this, I had this drawables buffer, so I say it has position, dimensions, and then texture coordinates, texture index. So texture coordinates is where in the texture image it is. Like I say, we're using our textures really as sprite sheets. So within the texture image, we're going to take a little quad out of it and apply that very simply to our graphics. Texture index is just, I have a bunch of those texture sprite sheets, so I need to tell you the shader which one of those it's referring to. For each drawable, we generate 4 vertices and 6 indices. So I have a buffer. Again, so if I come back into here, maybe actually the thing to do, let's get rid of that. Can I check out the tag? Dev 005? Not what I meant to do. Not local branch. Okay, that's not working like I thought it did. Can I git checkout? That not work? There we go. Okay, so this is the old state that the previous video was in. So you can see here we have our drawables, we have our single vertex buffer and index buffer. If I come down and I find called render frame, the first thing we do, we call draw drawables, which populates these buffers with some slightly hairy looking but ultimately fairly simple code. There's some handling in there around recreating swap chains, but we can see here we copy the vertex data in, we blank out the buffer of data, we copy the index data in, we blank out the index buffer. That's kind of it on the app side, right? We're going to copy this all over to the GPU, which we do somewhere in here. No? Yes, sorry. This is copying it to the GPU. So we've got a region of mapped memory. We copy the data over to that. Data now available to the GPU. There's some handling to get the next swap chain image. So this is about how we actually display to the screen. It's all to do with like the windowing system that your operating system makes available to us. And I think the next point we're looking for is where we start rendering. So there's a load of definitions. Vulkan's like this. There's loads of struct defining things. So a lot of this is details that if you watch the old videos from the Flectress series, I go through in great detail. But down here is the important point we call begin rendering. So at this point, we are starting to save in the commands that we're going to actually submit to the pipeline to do the draw. What else are we doing then? So we set the viewport and scissor, which is about how big the screen actually is. We bind our vertex buffer. There's one of them. We bind our index buffer. And again, there's only one of them. We bind our descriptor sets, which is about telling or making resources available to the shader. So in our case, this is describing all of our textures. And then we call command draw indexed, which tells it to use the index buffer and vertex buffer to draw to the screen. And then we end rendering and submit all of our commands, present to the screen. That's the old version of this. The, I guess, important details, if we kind of zoom out from that to see what we're doing, is we have a graphics pipeline, which is aware of the color attachment and depth attachment that the shaders are actually going to be writing into. So the color attachment is the actual image we're going to give to the screen in the end. The depth attachment is what's being used for depth testing so that we can do our writes in any order, but still get the correct kind of like Z level overlapping of things. And our shaders, it tells it about the vertex shader and fragment shader. It's a simple pipeline. Vertex shader just says, given these things coming in, how do I know what the actually, what does our vertex shader do? I was going to say it's about assembling primitives, but that might be the step before the vertex shader. Should we have a look? Shaders main vert. Yes, this GL position is just to say we're going to pass through like a special variable that is where is this this position, and then yeah, we pass through the other stuff that is on our vertex data point or our vertex structure that is needed for the fragment shader. So yeah, it's kind of data marshalling, and then the fragment shader does the draw. So that's all set up in the graphics pipeline. We have our buffer that has the actual like data for this frame, and then we have our descriptor set that is in this case just texture samplers. In a more complex program that could do more. If we come back, can I go check out main? Come back up here and just check that I see what I'm expecting to see. Which I am. So we've added this idea of sprite and mask. So at a high level, sprite textures are going to just draw literally what's in the texture image, right? If it's yellow, it becomes yellow. The mask textures are going to take in a 1 byte, it's like a single channel image, kind of grayscale image, and anything that is completely black in that image is completely transparent. Anything that's completely white is completely opaque, and then grey is a sort of gradient in between. Now, the way I've implemented it is I then say actually somewhere between 0 and 255 there's a threshold value, and above that we just consider on, below that we consider off, and our vertices already carry a color, so pass in a color, and if the pixel is on, it's that color. If it's off, it's completely transparent. It's kind of one thing if it's a mask, right? It's like the opposite of a stencil. It's giving you the things, the bits of the area that are going to be colored in with the color you pass in. If we go find that render frame again, down here, so you can see in here, we still do draw drawables, which calls this generate graphics primitives that should look very familiar from before. Right, so that logic's not changed, it's just been sort of repeated. But importantly, it needs to remember how many of each of those have been drawn. Right, so we're taking in those drawables, they're generating the vertices and indices, and we remember how many of each of those we've drawn. And then, like before, we need to copy that all over. So we copy into the vertex buffer and index buffer. And interestingly, we still only have one vertex buffer and one index buffer. I think in the first version of this that I sort of sat and thought about, I considered doing two. Like I've got two separate types of data. I think if the vertices end up carrying different data on them, you'd have to put them into separate places because they'll be different sizes. But you know, currently they work with all the same fields on them, and actually there's very little damage to having unused fields. So I think we're just going to like fat struct our way through this, and if you end up with unused data fields on certain things, there isn't really any pain unless we start pushing the hardware and having to like care more about using the cache more efficiently. So I'm not too worried, I don't think. We have the same guff around getting the swap chain set up and getting the next image. A bunch of setup that is the same as before, basically. We get down to our begin rendering again. So we keep scrolling down here. We get to our start rendering. We will set our viewport and scissor and bind our buffers. So down here we can see sets the viewport, sets the scissor, binds the vertex buffer, binds the index buffer. And again, the important point here is we only have to do this once. So I think I didn't read through the docs particularly carefully to double check this. I put it through like Gemini or something. But I think it makes sense. I think that binding vertex buffers and index buffers has a cost to it, right? So I guess the GPU driver has to marshal a bit of state around when you call this to say like, this is the thing that we're going to be referring to now. And so swapping one in for another has a non-trivial cost. And obviously you're calling this function every frame. You're calling this very quickly. So this is kind of like the hot path in your program. If there's anywhere that we care about it not doing stuff it doesn't need to do, it's here. So if we can get away with doing just the one of these, it's worth a little thinking to do that. The same goes to the descriptor set. So again, I think the first version of this that I thought of, I thought I was going to end up having to bind different descriptor sets for the two different like rounds of drawing. I guess jumping ahead. Spoilers, we're going to have 2 rounds of drawing. It turns out you don't have to. All right, so the descriptor set we bind just has 2 bindings on it. So we create a single descriptor set. I don't know if that's interesting to go back and find potentially. So if I go find, can I find where the descriptor set is getting made? Descriptor set layout, great info maybe. So you see there. So there's the single descriptor set has 2 descriptors bound in it, and one of them is our sprite texture combined samplers, and one is our mask texture combined samplers. and these bindings equal 1 and 0 are what we'll see in our fragment shaders. I guess I'll show you in a minute. So we bind the description sets, and then we need to bind our sprite pipelines. This is the first point that I guess is like significantly different. Is we no longer just have the graphics pipeline; we have to have 2 graphics pipelines. And the reason for that is, like I said before, the graphics pipeline knows essentially what shaders we're going to run at different stages in the graphics pipeline and where we're going to draw. And we want different logic for these 2 things, right? One of them is just going to draw the pixel values it sees, and one of them is going to do this threshold logic to say, if it's bright enough, we draw a color, and if not, don't. But again, I think surprisingly little difference between them. So can I find... Let me create... There we go. Create graphics pipeline. So we have this function. If I go grab references, it's called twice. Right. So once to make the sprite graphics pipeline, once to make the mask graphics pipeline. In fact, actually, you see in here, the only argument passed through that's different from between them is this shader module, right? So if we actually look in our code here, again, I won't go through this all in detail because the previous series goes through all of this in very like fine detail. But you can see, so like the vertex shader logic is literally exactly the same. We create a fragment shader stage. So this is the pipeline stage that runs at the fragment shader. And it is also essentially the same, just that it takes in the argument rather than the hard-coded single vertex shader. And everything else in here is the same, right? There's a lot of steps in here. There's a lot of logic about how we do all of our drawing. All exactly the same. It's just going to call that different thing for the fragment shader, which I thought was neat. I think that worked out easier than I thought it would. So we bind that pipeline. I don't know if there's a significant performance cost to that. I guess if you do know, I'd be interested to hear it in the comments. But like, so we do that. And then we do a first index draw. And then we're going to bind another one later and do another index draw. Then there's another point in here that, again, I've not gone through the docs carefully. I've not had a particularly like lot of time this week. So I'm planning to go back and read up on this. But I think it makes sense. The Gemini output suggested that I needed sort of like memory, some sort of resource usage synchronization. So we're going to bind one pipeline here that is going to draw, and if I remember right, is it the pipeline knows about the attachments, right? Like we said, the 2 pipelines have essentially the same setup except for the fragment shader they're going to use, which means they're both using the exact same attachments, which is what we want because we want to reuse the depth image information from the first index draw in the second one. Because if I draw something in front of a letter, that letter still needs to know that it's behind and get dropped in the early checks. So we have to create this memory barrier, and if we go and look at what that looks like, is that easy to go look at? So memory barrier 2, I think it's memory barrier 2 because it's using synchronization 2. So this was a mild irritation. It turns out, so I think Vulkan 1.4 adds synchronization 2 to core. So anything that supports the 1.4 API must support synchronization 2. It's not enabled by default. It took me an annoying amount of time to realize that was my issue. So you have to go and pass that in at device creation. So it's lesson learned. Remember that. But I can't remember how this works. Color attachment output and late fragment tests. So I think the way I got these was I added the access masks that I cared about and then ran it. The validation checks told me which stage masks I was. So like I said, hopefully I'll get a bit of time this week and I can go read the docs and check this makes sense. But I think this makes sense. So the source is going to be doing color attachment rights and depth stencil attachment rights. And the destination, which is our second draw, needs to do color attachment rights and Oh, have I not got a color attachment read? Because it doesn't do any reads. Right, it's just writing to that value. It's not doing any like alpha blending, so it doesn't need to read the existing value. Depth, stencil, attachment, write, and read, because it's going to do reads on that value to do the depth test. So what we're saying here is that we're going to do one draw, and then I'm going to do another draw, and the second draw can't do any color attachment writes, color depth attachment writes, or depth attachment reads until after the source stage has finished its color attachment writes and its depth attachment writes. Those dependencies are by region, which means that if you imagine, like, because the GPU performance win is that it's all super parallelized, it's doing these calculations across the whole screen in parallel, essentially, right? As fast as it can. So we don't need to wait for all of the first round of drawing to finish before we start the second round of drawing. All we need to know is that this chunk of the screen has finished its first round of drawing. Then that chunk of the screen can start on the second round of drawing, even if the first round of drawing is still ongoing elsewhere. Is if I've understood it right, what that means. So that's our synchronization. To be fair, I think if I took this out, I didn't see any issues, but I think logically this makes sense. So yeah, like I say, if you're a game engine person and you know about these things and this doesn't make sense, please let me know. But I think this makes sense. Yeah, and then after we've synchronized, we bind the other pipeline, we do the second draw, we end rendering, and then, unless my notes tell me otherwise, I think everything's the same. Yeah, we end the render, we submit, we present the screen. So, yeah, that's enough, it turns out. That lets us use two sets of data with two different fragment shaders. I guess one point I've not made in here, we have two sets of data, but we only have one buffer still. The way we pull that off is we remember how many of these things we draw, and then I think it's in this indexed draw here, we have to tell it the number of these things we want to draw and where the first index in that buffer is. So this is something that's explicitly kind of encouraged and included in the Vulkan API, I assume, because the performance win is real, and therefore more complex games that need to care about these things will want to work in this way as well. So we see here the sprite draw uses the sprite drawables for the index count, and its first index is 0. This second draw down here uses the mask drawables count, and then the sprite drawables count to work out where its first index is. If we have more of these in future, I guess you just have a cumulative count that tracks up as you go through. And that's how you manage that. I guess it's also interesting to go and have a quick look at my fragment shaders. And I'm trying to remember what I've called them. I think I've called them sprite. Yeah. So this is the fragment shader. Do I have a GLSL mode? I trigger C mode because I think it's C-like. So this is the old one. They're very similar, so this shouldn't be too scary. In fact, can I pull this up? Go get my mask frag as well, so you can see them next to each other. We'll C-mode that as well for neatness. And you can see they're very similar to each other. So they both have this block, frag color A. So we're going to use the alpha channel on our color that's passed in on the vertex to tell whether or not this is being overridden. So my vertices have a override color that's useful for debugging. So if I come in here and I run this, you'll see me do this a bunch of times if you watch the other videos. Let's imagine this A wasn't showing up. What I can do is I can set the override color. Actually, we do it. We go to main.odin. We find drawable A. Its color is already set to blue. If I set override color to true, it just fills in the entire thing blue, so I can see actually where my primitive is. I set it back to false, then it actually draws the thing. So they both have that, because I found that's really useful. Then the simple sprite version then does our sampling, and then this is how I'm doing what I've been calling windowed transparency. So I'm not doing any alpha blending to draw a thing over another thing, so you can see the second thing through it. Mostly because I don't think our sprite style is going to need that. But we do need to be able to have like transparent bits so that not everything has to be a square. And this is how we're doing it. We're doing discards because it makes it not just not color this pixel, but it also makes it not write to the depth attachment, which means that we don't mess up our ordering. The tweak made here is we set this threshold. This might be something we actually want to pass through on the vertices. We'll have to wait and see if this is something that needs to be set per like thing we draw, or if it's a rule that just applies across all our fonts. Because currently this is only being used for fonts. This may end up being useful for other stuff, but for now it's just fonts. So I think we might be able to get away with just a general value in here. Stuff there for debugging. What am I doing here? I go and read my sampled value. And then we say here that if the sampled value's alpha channel is less than 1, we might not even need that because that should never get hit. That's interesting. I'll have to think about that. But the important part here is if the sampled color .r is less than threshold. So because these are single byte values, when we read the sampled color off of it, actually only the R channel should be populated. So we go and read the R channel, and if it's less than our threshold, we discard, so it becomes transparent. Otherwise, we go in and say that our out color RGB values are the value that's passed in on the shader. So we use the same color as we use for the override, and the out color alpha is set to 1, which means completely opaque, so it will draw. I'm actually not sure if that does anything, but conceptually it's what it's doing. Check that as well. But yeah, that's how the two things work. I think it might be interesting to just show quickly if I go to here and we start up render doc. Partly because I thought this was fun to see. I load my settings in here. We'll save a frame. If you're at all interested in all of these sorts of things, I don't know, render doc's really cool. Well worth playing with. So the thing that's useful to do in here, if we right click on here and you go to history, we can see how this pixel ended up the color it is. So obviously this is the one with our override color on it. We can see here color pass 1. Can't remember what these expanded bits do. So you can see, what can we see? We have a begin rendering that does a clear. We have a command index draw. That's 2 fragments touching it because there's the shape with the first, like this pink square, and then there's also the shape with this yellow circle. And so the first one goes through and makes it pink. The yellow circle comes through afterwards and is in front of it because its depth is greater. So it goes from pink to yellow. And we then have the second pass, do a draw. Go to our box here, and it makes it blue. If I come into here, you can see, so there's some filters on this. So this action is only showing us the steps that actually do something like actively interesting where we might want to inspect the outputs. We can see here that first clear. Then we can see the image after the first draw. You can see all the textures that are bound. So this was the old Flectris texture, which is being used to draw this box. This gradient and this circle are just other random things I drew. And again, you can inspect, I think, the history at this point if you want to see what's going wrong. And then we get to this point, and you can see in here our texture. Like I say, it's only the R channel that gets populated, so it looks red. But yeah, you can go pick a point. So like this one will be inside of the box for what? So it's only inside boxes for this E18 primitive, I think. Is that what that's saying? I'm not sure. I would have thought, okay, yeah, no, I was right. So it's inside the box for this green square, and then it's also inside the box for the B, right? Because you have to square this out to see where it actually is. Again, you can see that if you go to the mesh viewer, you can see all of the stuff. How do you do it again? Solid color, don't highlight vertices. And then you can see the mesh that's being used for each draw. So this is the draw that's just doing our sprites. So this one here with the two on top of each other, that would be this square with this circle on top of it. And then if I come into this second one, you can see we've only got the two because we're drawing two letters. So, all very cool. And then you can see our discard happening here. So shader executed discard is what it says when you hit this keyword. So how cool is that? What else did it say? I think that might be it for what we got up to. I'm actually quite pleased with this as I think this looked far messier when I was first starting at it, and then it's kind of chiseled down to, I think, quite a neat little solution overall. I think this extends quite neatly as well, so if there's more of these in the future, we can work it out. But yeah, I think that should cover our needs. So the next steps, we're going to have to have a bit of a think. We can draw a letter. We can't yet draw a string easily. So the font info from STB TrueType I've kept like in memory. I've not freed. And I've done that because it means we can keep the kerning information. So I think potentially next would be to look at a function to draw a string nicely, which would be, to say like, I want to draw a string at this position, and then work out how we want to do sizing it and how we want to do positioning the characters relative to each other to make them look nice. And if we get that working, that I think covers everything for the first round of the game, because, like I say, we're going to do a roguelike. We're going to start with ASCII graphics, so it all should be letters in a grid, and strings of text to communicate to you. So that should be pretty fun. I think the only other thing I might do before that is in the Flectris code, basically just positioned everything very manually. I think it might be worth a bit of a think about how I organize that code. I don't want to build like a big abstraction around it all. So I think the CLay author has a series of videos on YouTube explaining how he basically does like a Flexbox style algorithm, which might be interesting to do, but I don't know. It feels like I should probably do something that's less than that first and see if it gets painful, and then we'll kind of build our way up toward that. So I'm not really sure what to do with that, and it may influence how we want to do our string layout. So I'll have a think. But they're the two candidates at the minute for what we're going to do next. I guess we'll see in the next video what I land on. I think it might be a bit of a half dozen of one, six of the other, because I think they all land in the same place at the end. Once we've got those two done, I think we're ready to start actually building out our game. So that's exciting. Yeah, I think that is everything I wanted to say. So let me just check I've not got any silly things in there. I'll run the thing again so you can see my very pretty letters. And yeah, I look forward to seeing you on the next one. If you've made it this far, I'd be very curious to hear what you make of this video that's not live coding. Because like, if you watched the previous video, you'll know this is a new way of doing this for me. So I hope it's interesting. I've not waffled too much. But yeah, I will look forward to seeing you with the next update.